Okay, so in this video, we will consider the third possibility in the case of an improper integral of type 1. And that is, if we considered the integral of f of x dx, assuming f is continuous on the entire real line, and we try to evaluate the integral of f from negative infinity to positive infinity, so where both bounds of integration are infinite. Now you may ask, well, how could we define this improper integral in a similar fashion as we did in the previous examples where we had only one infinite bound of integration? And it might be very tempting to define it in the following fashion. So you could integrate f of x symmetrically about 0, that is from negative t to positive t, where t is a positive variable. Clearly these are not equal, but as we let t approach positive infinity, it looks like this should work out. As t approaches positive infinity, well, t approaches positive infinity. As t approaches positive infinity, negative t approaches negative infinity. So this looks pretty good. And actually there is something wrong with this. So this will not be our definition for this type of improper integral. What we have to do, and we'll see why very shortly in an example, there is something wrong with this symmetric interval from negative t to t being symmetric about 0. What we have to do is let both bounds of integration approach independently of one another, positive and negative infinity. So here's how it should be done. So we should integrate the function f from, say, s to t, where s and t are independent variables, and then we will first let t approach positive infinity, and of course then we'll take the limit as s approaches negative infinity. And letting both bounds of integration approach positive infinity in case of t and negative infinity in case of s independently of one another is the way to do it. It's worth noticing that you could of course swap these two limits. You could first let s approach negative infinity and then t approach positive infinity. So you could swap the order of these two limits. And this is the way to do it. Let's see why in some cases there could be something wrong with this. In a lot of cases, both will actually return the same answer, but not always. So let's see why we rejected this simpler looking definition in favor of this rather seemingly more complicated definition. And we'll take very simply f of x to be equal to x. So if you sketch the graph of y equals x, this is simply a line of slope 1 passing through the origin, so a very simple function. And now, let's look at our first naive definition and see why it is indeed a naive definition. So we say, okay, well, we would try to make sense of the improper integral from negative infinity to positive infinity of x dx. If we go with our naive definition, we let t approach infinity, and we integrate from negative t to t x dx. Well, let's look at this geometrically, and we'll see that we already know the answer without doing any further work. So our interval is symmetric about 0. So we go up to t and negative t. So geometrically, if you look from 0 to t, we will obtain the area below the curve y equals x from 0 to t. From negative t to 0, as the curve is negative, we will obtain not the area, but the negative of the area of this region. But as we integrate from negative t to t, and clearly the function y equals x returns from negative t to t two regions with the exact same area, this will return, without the limit now, the area of this region minus the area of this region, which will always be 0 as our interval is symmetric about 0. And let's verify this. So, once again, we can apply here the fundamental theorem of calculus as the function x is continuous on the finite interval from negative t to t. So we find our antiderivative, x squared over 2, and we evaluate from negative t to t. We evaluate at t, so we get t squared over 2, minus, we evaluate at negative t, but negative t all squared is positive t squared over 2. And so you see, for any choice of t, no matter how large, t squared over 2 minus itself is equal to 0. And so now we have a trivial limit. We are asking, what happens to 0? As t approaches positive infinity, the answer is, of course, 0. 0 is always 0. And as expected, we already knew that the answer would be 0 from the geometry of the problem. But if you look here, there is something kind of wrong with this equality, right? There's nothing wrong with this being equal to 0. This is perfectly fine. But if you look at this being equal to 0, there is something slightly unsettling. If you cut this into two parts, the first from negative infinity to 0, so if you took the whole negative of the area, you would get negative infinity. And if you then went from 0 to positive infinity, take the area of all of this region, you would get positive infinity. So in a sense, by using a symmetric interval about 0, we end up with what essentially is a statement that positive infinity minus infinity is 0. And this is the problem. As both, if I bring this over here, this will make it more explicit. If this existed, which it seems like it does, we should be able to break it up from negative infinity all the way up to 0. So we'll make a stop there. And then plus, and we'll add what's left over from 0 to infinity. But as we said, it's clear that this, you can evaluate if you want, will equal negative infinity, plus this, which is the area of this region now, will equal positive infinity. And that's where the problem is. If this really indeed did exist, we should be able to break it up into its two parts. The first half from negative infinity to 0, and then the second half from 0 to infinity. And as we add both pieces, we should obtain the exact answer. But what's unsettling here is that this answer is the area of this region, which is positive infinity, and this answer is the negative area of this region, which is negative infinity. And so we have, it seems, a statement that positive minus positive infinity minus infinity is 0, and that's where the problem is. Let's see what happens if we now use our second definition. Again, as both s and t are fixed constants, and the function s is continuous, we can use the fundamental theorem of calculus here. we'll have x squared over 2. Apply that t will give us t squared over 2. Minus x squared over 2, our antiderivative, applied at s, minus s squared over 2. And now if we handle the limit as t goes to infinity first, this will go to positive infinity, minus s squared over 2. But no matter what the value of s is, this will be infinity. And as you now try to let s approach negative infinity, it's not possible as the first limit does not exist, which is again this part right here, the positive infinity. And for this reason we say that the improper integral here actually diverges. And that's the reason why we have to go with this way of breaking down this type of improper integral instead of the symmetric way of doing it. Now, if both limits would give you something that would exist, then the improper integral would converge. And that's it.